Let's go ahead and start that guy. So we were talking about the rate of reactions, right? How we measure reaction rates, okay? And so it has a couple names. I call it rate of reaction. I also call it reaction rates, okay? And again, this is just the overall speed of a chemical reaction. So let's say we do have our nice little chemical reaction where we have some sort of reactant A going to make a 2B, okay? If I wanted to measure the average rate of the reaction, I could measure it by either monitoring the change in concentration of A as a function of time or the change in concentration of B, right? And so if I monitored the change in concentration of A as a function of time, I would be looking at delta, so change in concentration of A over change in time, right? That would be the relative rate of change of A. Would that be a negative or a positive, since it's a reactant? It would be negative, right? I don't want to deal with negative rates, so what do I do to try to get rid of that negative? Not try to, but just get rid of it. I put a negative in front, right? Because this guy, because it's a reactant, overall is going to be a negative. To get rid of that negative, I just put a negative in front, so I get an overall positive rate, okay? So I can measure the rate of this reaction by watching A, right? And then putting a negative in front, getting my rate of reaction. I could also measure this rate of reaction by watching what's happening to B, right? But what's happening to B relative to what's happening to A? So B is appearing, so we're going to have a positive in front of B because essentially we're going to get a positive delta B over delta T, right? But what also is happening at the same time? For every one A I'm losing, how many B's am I getting? 2, right? So if we just sat there and watched B, we would measure a different rate of change than what we saw for A. We don't want that. We want an overall average rate of reaction. And so to counteract for that, I'm going to put 1 over whatever the stoichiometric coefficient is in front to essentially normalize it and account for just the production or the disappearance of one molecule of a thing, okay? So then, if I'm measuring the average rate of change with respect to B, for the reaction, I can do that. This is my relative rate with respect to B. I just have to put that plus 1/2 in front to account for the fact that 2 of them are forming for every 1A being lost, okay? So, a couple of things I wasn't super clear about, and I just kind of want to formalize with respect to vocabulary, okay? This guy, what we're measuring, again, usually we're measuring an average rate of reaction. So average rate of reaction. These guys, though, are something that we call the relative rate of appearance or disappearance, okay? So anytime I talk about relative rates, I'm talking about, oh, what's happening to A, what's happening to B, okay? So again, this is the average rate of the reaction. This is usually how we're going to be measuring this. So this is going to be the rate of change over a specific time interval. How does this differ from the instantaneous rate? So the instantaneous rate, again, just as a reminder, was essentially the slope of the tangent line at whatever point in time we wanted to measure the instantaneous rate. It's slightly different than the average rate, but as long as this delta T is fairly small, the average rate will approximate the overall rate of reaction at whatever instantaneous point we want to look at, okay? All right, so a couple more things. This thing, overall, is called the rate expression. So there's a lot of vocabulary early on, and you kind of have to get some of these words and terms clear in your mind, okay? So average rate of reaction, relative rate of change, and then the overall rate expression, okay? Okay, so that's just a reminder. We're going to move on. What were a couple of the factors that affected the rate of reaction? So I introduced you to one really early with respect to the lizard, right? What was the factor that influenced that rate of reaction? Temperature, right? So temperature was one of those things that affected reaction rates. So the whole idea behind this, as we raise the temperature, what happens to the speed of the molecules? They move faster, right? That increases the probability of collision, which is going to increase our reaction rate. What was another thing that increased or affected the overall reaction rate? Concentration, okay? And so concentration And the effect of concentration on the rate of reactions is what we're going to talk about at the beginning of tonight, okay? How concentration can have an overall effect on the rate of the reaction, okay? So in general, if we increase the concentration of our reactants, what's going to happen in theory to the rate? Should go faster, right? So there should be what we would call a direct proportionality between concentration and rate, okay? We will find that this is not always the case. This is not always a direct proportionality, but for the most part, that's what we're going to move forward with, okay? Okay, so how do we actually determine how the overall concentration of reactants affects the rate of the reaction? Okay, we utilize something called the rate law. Okay, so we start out with a really nice introductory rate law where we have a reaction that only has one reactant to it. Okay, so for this reaction, our single reactant is A. Okay, the rate law for this takes the form of this, where we have the rate is equal to this little lowercase k, this is called the rate constant, it's going to be a constant of proportionality, times the concentration of our reactant, A, raised to some power, okay? This power, is called the reaction order. And this is essentially where this proportionality comes in, okay? So this can be direct proportional, it can also not be proportional at all, and it can also be proportional to A squared. Okay, so N is reaction order, K is just going to be a constant of proportionality. Okay, so what are the various possible values in this reaction order? Okay, so there are going to be three that you guys should know and be comfortable with. Okay, first one is N is equal to 0, and we'll talk about that. Second one is N is equal to 1. Third one is N is equal to 2. Okay, there are other orders possible. This is not the only possible orders that there are, including fractional orders, and so you should note that, okay? All right, so let's essentially consider what happens when N is equal to these various numbers, okay? So for example, if N is equal to 1, what happens to the rate law? So we go ahead and substitute if N is equal to 0, we go ahead and substitute that in, we get K times concentration of A raised to what power? If we're doing N is equal to 0. 0. What is anything raised to the 0 power? 1, right? So what happens to the overall rate law here? Rate becomes equal to just what? K, right? So if N is equal to 1, this is called a zero order reaction, okay? Or zero order with respect to whatever reactant we're looking at, and essentially the rate has nothing to do with the concentration of that species, right? So if we increase the concentration of A, what's going to happen to the rate? Nothing, right? The rate is going to be constant throughout because it has nothing to do, it's a zero order reactant, okay? All right, so what happens to the rate law if N is equal to 1? So we can go ahead and substitute that in, A to the first power, okay? So now, is there a proportionality between the rate of the reaction and the concentration of A? Yes, right? What happens to the rate of the reaction if I say double the concentration of A? If I double the concentration of A, the overall rate of the reaction should also double because these guys are directly proportional to one another at this point in time, okay? Now what happens if N is equal to 2? So we can go ahead and substitute that in. Rate is equal to K, A, raised to the second power. This is called a second order reaction, okay? If I double the concentration of A in a second order reaction, what's going to happen to the overall rate? What is 2 raised to the second power? 4, right? So if this was a second order reaction and we doubled A, what we would see is instead of a doubling, a quadrupling of the overall rate because again, 2 squared is 4, okay? Okay, so these are the ones that you should be familiar with: zero order, first order, and second order. Okay, so how do we actually figure out these orders with respect to these rate laws, okay? Number one, these have to be determined experimentally, okay? You can't just look at an overall chemical reaction and say, oh, I think it's going to be first order, or I think it's going to be second order, okay? How are we going to actually determine this experimentally, though? If we go back to the rate law, rate is equal to K, A, and we're trying to figure out what N is. What are our various variables here? What can we control? Can we control the rate of the reaction? No. But what can we control? Right, so we can control the concentration of A. What can we measure as a result of that? Rate, right? So we can measure rate. We have now a means to measure the overall average rate of a reaction, okay? So this is how we experimentally determine what the order of these reactions are, is we control A, we measure the rate, and from that data, we can figure out what N is, okay? All right, so let's show a couple of examples of how we would do that. All right, so let's say we had a reaction. Again, we have a single reactant, so A, and we went into the lab and we ran 3 separate experiments, okay? So in experiment 1, we went with some initial concentration of A and we measured the rate. Experiment 2, we went with some initial concentration of A, we measured the rate of the reaction, and then in experiment 3, same thing, we measured the rate of the reaction. Okay, so note, what do I do in going from experiment 1 to experiment 2? What do I do to the concentration of A? I double it, right? So for this one, I double the concentration of A. What happens to the rate of reaction? Nothing happens, right? It stays the exact same. So from this data, right, because this is my reaction rate, it's the same number. From this data, if I double A and nothing happens, what could I conclude about the order of that reactant? 0, right? So for this one, rate would be equal to K, A to the 0 power, okay? All right, so then what happens if we do the exact same thing? Different experiment, have 3 different reactions, and this one, again, I double the concentration of A, and going from experiment 1 to experiment 2, what happens to the rate? It doubles, right? So if I double A and the reaction rate doubles, what can I assume about the order with respect to this reaction? Right, so this would be a first order reaction, and our rate law here would be K, A to the 1, okay? So last one, what about this guy? Same thing, and going from experiment number 1 to experiment number 2, I double A, what happens to the reaction rate? Yeah, it increases by 4, it quadruples. So what is the order with respect to this reaction? Second order. So rate is equal to K, A to the 2. Okay? This is what I mean about us experimentally going in and determining these reaction orders. We have to essentially go through, do a bunch of different experiments where we vary the concentration of our reactants, we measure the rate, and from that data, we can figure out what these orders are. Okay? Okay, so that was nice and easy. Why? Because there was only one reactant, right? What happens if we move on to reactions where we have multiple reactants? How are we going to figure out the orders of each of those? Because again, ideally, each of those are going to have their own effect on the overall reaction rate, okay? So again, we're going to have to do experiments, and I'll show you what I mean by that in the next slide. A couple of things to note here. Again, these little orders, we have to determine them experimentally, and then the overall order of the reaction is going to be the sum of whatever these exponents are, okay? So if A was first order and B was second order, then the overall order of the reaction would be 1 plus 2, which is 3. It'd be third order overall, okay? Okay, so how are we going to do this? How are we going to figure out the orders when we have 2 things that we have to consider? So what we're going to do, we're going to do something very similar for what we were doing for the one reactant, except now what we're going to do is run more experiments, and we're going to hold one of the things constant while we vary the concentration of the other thing, and we're going to look what happens to the overall rate, okay? So what do I mean by, well, let's see, okay? So let's say that we're trying to figure out the orders with respect to NO2 as well as CO for this reaction, okay? So we know that the rate law here is rate is equal to K NO2, but we don't know what the order is, so we'll just leave this as an X. And then CO, we don't know what the order is, we'll leave this as a Y, okay? So how do we figure out what this X and Y are? And then correspondingly after that, we'll be able to figure out what K is. That's kind of what the questions are with respect to these types of problems. So what we're going to first do is we're going to look at our various experiments that we have. So we've run 1, 2, 3, and 4, okay? If I want to figure out the order with respect to NO2, I have to find 2 experiments where I vary its concentration in some way while holding the other thing constant, right? So if I look at experiment 2 versus experiment 1, what do I do to the concentration of NO2? I double it, right? What happens to CO? What have I done in those experiments? I've held it constant, right? So if CO had some influence on the rate of the reaction, it wouldn't actually manifest itself here because it's the same for both of these reactions, okay? So for this guy, I've doubled NO2, I've held this guy constant. What happens to the overall rate of the reaction? It quadruples, right? So 0.0082 divided by 0.0021 is equal to 4, okay? So if I have a doubling of NO2, I hold CO constant, and the rate quadruples, what can I assume about the order with respect to NO2? Should be second order, right? So NO2 should be second order. Now, if I want to figure out the order with respect to CO, I need to find 2 experiments where I double its concentration, or I do something to its concentration while I hold the concentration of NO2 constant. So what are those 2 experiments?
2 and 3.
Right, so if I look at 2 and 3, I have a constant NO2, so we've taken out any influence it's going to have on changing the rate. So this guy's constant. And for CO, I've doubled the concentration, right? So when I do that, what happens to the rate of the reaction? Nothing, right? Within the experimental order of the experiment, or the experimental error of the experiment, this does nothing. It's essentially the exact same rate, okay? So if I double CO, hold NO2 constant, and the rate doesn't change at all, what can I assume about the order with respect to CO? 0 order, okay? So CO would be 0. All right, so our rate law for this would be rate is equal to K NO2 to the second. We could also write CO to the 0, but what else could I just leave that as? Just K NO2 squared, right? I don't even have to include the CO because it's 0 order, it's just a 1, okay? Okay, so how do you think I'm going to find the rate constant? Because that's part B. So note what I know now, right? I have a bunch of experiments where I've measured rate, I've measured the concentration of things, and I also now know the order, right? So to figure out what K is, all I'm going to do is pick an experiment, okay? It can be 1, it can be 2, it can be 3. I almost always pick number 4, just because it's the closest to where I am. I plug in the values for all of those various things, and I solve for K, okay? So when I do that, my rate for number 4 is going to be 0.033. What are the units for this initial rate? Molar per second. This is equal to K times the concentration of NO2 in experiment number 4, okay? So this is 0.40 molar squared, okay? So now I've plugged in everything. All I have to do is solve for K. To do that, I'm going to divide by 0.40 molar squared, 0.40 molar squared. And that's going to give me K equal to, and I've done this in theory, K equal to 0.21, but now I need to consider units because the K's with respect to units are very particular. Okay, so what do you think my units are going to be for this K? So note I have a molar on top, right? What is another way to write M over S? So I've been writing M over S. Another way to write this would be MS to the what power? -1, right? So I could essentially have that on top. I have two m's on bottom, right? So how many m's are going to get canceled? 1, right? And so what am I going to be left with? I'm going to have 1 m left, but it's going to be in the denominator, right? So this would be m to the -1, and I still have that s to the -1, okay? So the units here would be inverse molar, inverse seconds. Another way, again, to write that would be 1 over m times s, okay? So units are important with respect to rate constants, I promise. Okay, I want to do one more thing, and then we're going to do an example, because sometimes what's really nice about this problem is that everything's perfect, right? We completely double the concentration, it quadruples the rate. A lot of times, these aren't going to be super perfect, right? It's not going to be so obvious about what the order is. So I'm going to show you how to solve for it when it's not super perfect, and then we're going to do an example problem, and then we'll move on to the activity, okay? So we're going to do this problem again, but I'm going to show you again what happens or how to solve for this if these doublings and quadruplings weren't exactly perfect, okay? And that's good. At least I made some room for myself. Okay, so we already know CO. We're just going to ignore it for the most part because we know it has 0 order. And I'm going to show you how to get the 2, again, when this isn't perfect. So what 2 experiments did we compare to get the order with respect to NO2? 1 and 2, right? So we compared number 1 to number 2. What we are really doing here is we are comparing the ratio of the rate laws of the 2, okay? So what do I mean by that? I'm going to take the rate law for experiment 2 with unknown orders. We don't know what the orders are. So this is going to be rate for experiment 2 is equal to K times the concentration of NO2 in experiment 2 raised to our unknown power, concentration of CO in experiment 2 raised to its unknown power, and we're going to essentially take the ratio of the same rate law for experiment 1, okay? So experiment 1 would be rate of experiment 1 is equal to the same K. Now we'll be dealing with the concentration of NO2 in experiment 1 and the concentration of CO in experiment 1. That's what I mean by these little 1 subscripts, okay? Now I'm going to plug all of the information I know in, okay? I know these 2 rates. So rate of experiment 2 is 0.0082 over 0.0021. K's are the same, so KK. And then we have concentration of NO2 in experiment 2 raised to the X power concentration of CO in experiment 2 raised to the Y. And I do the exact same thing for experiment 1 and 0.10. Okay, so now we've plugged in these guys, we've plugged in all the numbers. I can start to simplify a few things, okay? So this guy, this is just a ratio of rates. What is this number if we divided? 4. So 4 is equal to, we have the same exact K, like the K doesn't change, it's a constant. So can we cancel those? Yes, we can. So this guy's going to go away. What about the concentration of the CO? It's the same number raised to the exact same power. Can I get rid of those? Yes, right? I got this guy, I got this guy. So what we have left is 0.20 raised to the X divided by 0.10 raised to the same exact exponent. Can I condense these two? If you have a number raised to an exponent divided by a number raised to the exact same exponent, can I just divide those numbers? Yes. So what does this condense down to? 2 raised to the X. Okay? I know it's like, oh, this is obvious, right? But trust me, this is how you're going to do it when it's not super obvious. Now, what this little expression or this equation is saying is 2 raised to some number is equal to 4, right? It's easy to see, well, that number has to be 2. But what if this wasn't like this? How would you solve a problem like this? Right, take the logarithm, okay? So what you do is you take log of both sides, log of both sides. On the left, we'll be left with log of 4, which is just a number. You push 4 into your calculator, and you push log, it gives you a number. What happens to this guy? Log of 2 raised to the x. What does that turn into? So law of logarithms, this makes it x times log of 2. The x comes out of the exponent, and it becomes just a normal, simple variable, okay? So log of 4 is equal to x times log of 2. How would I solve for x here? I would just divide by log of 2, log of 2. And amazingly, when you do that in your calculator, x equals 2. Okay, all right, so that's the real mathematics behind what we're doing. What's super easy is, again, if things double and they quadruple, you don't have to do this, right? This is only going to be useful when, oh, the concentrations were like 3.5 and the rate was like 6.9. How do I get an order out of that, okay? Okay, so I'm going to let you guys go ahead and do a problem. Okay, so this was the problem that we ended with last class. So this was question 14.2, where I give you a bunch of experimental data, and you guys are supposed to determine the rate law for the reaction as well as the rate constant. Okay, so I'm going to go ahead and go over the solution to this problem because we didn't have enough time in class. And I'll probably start by going over this problem in class anyway, so we'll do this again, but I just want to make sure that I have it in a recorded format, okay? All right, so for this problem, we're wanting to determine the rate law for this reaction, okay? So this reaction has 2 reactants, and so we know that the rate law is going to take the form rate is equal to K, the rate constant, times the concentration of our first reactant raised to some unknown order times the concentration of our second reactant raised to some other unknown order, okay? And so we're going to utilize this data here to determine what these orders are, what the order is with respect to CHCl3, and what the order is with respect to Cl2, okay? So for the first one, I'm going to look for the order with respect to CHCl3 because that's going to be the easiest one for this problem. Okay, so to do that, to figure out the order with respect to CHCl3, I need to find 2 experiments where I do something to the concentration of CHCl3 and I hold the concentration of Cl2 constant, right? I'm looking for the effect of changing the concentration of this guy. To make sure that I don't introduce any effect from this guy, I have to find 2 experiments where I hold a constant. So here we have this guy, constant, so the other reactant, between experiments 2 and 1, we haven't changed the concentration, but we go from experiment 1 with a 0.01 molar and experiment 2 with a 0.02 molar. So we have doubled the concentration of our reactant that we're looking at. Okay, so experiments 1 and 2, we doubled the concentration of CHCl3, we hold Cl2 constant, and we should be able to determine what happens to the overall rate, right? So if we take this guy, 0.0069, and divide by 0.0035, we find that that is pretty much a doubling. So 0.0069 divided by 0.0035, it's equal actually to 1.97, which you can round up to 2. Okay, so in experiment number 1 to experiment number 2, we have doubled the concentration of CHCl3, we have held Cl2 constant, and we've seen a doubling of the rate. So a doubling concentration leading to a doubling of the rate. This is going to be first order with respect to CHCl3, okay? So that's number 1. We can put in rate is equal to K CHCl3 to the 1. Now we need to figure out what the order is for Cl2, okay? So in this one, we're going to look for 2 reactions where we have held the other guy constant. So where we've held this one constant and we've done something to the concentration of Cl2. So we go between experiments number 2 and experiment number 3. We have held CHCl3 constant and we have doubled the concentration of Cl2. So we're looking at what effect doubling this concentration has on the rate. We have to hold the other thing constant. And so we look, when we double the concentration of Cl2, it doesn't quite double, right? So when we compare this 0.0098 to 0.0069, we get an increase of about 1.42 times in the initial rate, okay? So this is going to be one of those ones that isn't perfect. It isn't exactly what we would expect. And so we're going to have to go through this to figure out what the actual order is here by using this ratio of rate laws, right? So I kind of introduced that, the actual math that we're doing when these guys aren't exactly perfect. So what we're going to do is we're going to compare the rate laws of experiment number 3 and experiment number 2. Okay, so I'm going to start with the rate law for experiment number 3 on top, because that usually is whatever's the biggest one, so whatever gives me the bigger rate and the bigger concentration, I always like to put that on top so that I am dealing with whole numbers instead of fractions. I'm going to compare that to the rate law for experiment number 2, okay? So this is the ratio of rate laws, this is what I'm talking about. So for the rate law for experiment 3, we'll go ahead and put in the K, which is constant, and it will go away when we take this ratio. And then I'm going to go ahead and put in the concentration of CHCl3 for experiment number 3. We already know this is to the 1 power, and then the concentration of Cl2 for experiment number 3. This is going to be to our unknown power. And we're going to compare that to the same exact thing, only for these concentrations with respect to experiment 2. Okay, so I haven't actually put in any real numbers yet. I'm just writing out what rate laws, that's a 2, that we're going to be comparing, okay? So now I've written out this ratio. I'm going to go ahead and plug stuff in. So the rate for experiment 3 is 0.0098. The rate for experiment number 2 is 0.0069. This is going to be equal to K, some unknown, times the concentration of CHCl3 in experiment number 3, 0.020. This is raised to the first power because we already figured that out, times the concentration of Cl2 in experiment 3. So this is 0.020 raised to the y. So then I'll go through and do the same thing for experiment 2. This was also 0.020 raised to the first power, and then this guy, Cl2 in experiment 2, was 0.010 raised to the y. Okay, so now I'm going to go ahead and simplify things. When I take this ratio, this simplifies to 1.42 is equal to, the k's will cancel when we divide, the 0.020 will cancel when we divide, and we're going to be left with 0.02 to the y divided by 0.01 to the y, which simplifies down to 2 to the y power. Okay, so to figure out what y is, to solve this, we're going to go ahead and take the logarithm of both sides. So the log of both sides, and just as a reminder, the log of 2 raised to a power is equal to that power times the log of 2. So that's going to allow us to simplify the expression on the right to y times log of 2. To solve for y, I'm going to divide by log of 2. Log of 2. And just note that log of 1.42 divided by log of 2, these are just numbers, right? A log of something ends up just being a number. You push the number, you push the log button in your calculator to give you that. So when you do this, you'll end up with 2, or no, not 2. You'll end up with 0.51 is equal to y. So this is what I mean when I say a fractional coefficient. Again, this 0.51 would round down to just 0.50, or we could just say a 1/2 power, okay? So on an exam, I will not give you a fractional coefficient. I will not give you a fractional order, but this is kind of for fair play because, you know, I'm showing you the hardest possible examples here, okay? Okay, so then the rate constant, now that we know the order with respect to Cl2, the rate constant here is going to be rate is equal to K CHCl3 to the 1 Cl2 to the 1/2, 1/2. Let me actually make that a little prettier. 1/2. Okay. And so then the last little bit of this is determine the rate constant for the reaction. So I'm going to go ahead and erase this guy and give myself some room. So with respect to rate constants, once you have the rate law, you can pick any of the reactions, plug in the values, and determine what little lowercase k is. When you actually do this experimentally, and we'll do this in the lab, you don't actually just pick one. You'll actually find k for all 4 and then take an average. That'll be the average k. That'll be like the rate constant overall. But with respect to actually doing this on homework, doing this on assignments, you're just going to pick one and go with it. They should all be fairly similar with respect to one another. So I'm going to pick the data from experiment 4 to plug in. So then experiment number 4, the rate here is 0.027. The units are molar inverse seconds, right? 1 over m over s. This is going to be equal to k times concentration of CHCl3 in experiment 4, which is 0.040 molar raised to the 1 power, and then the concentration for Cl2, 0.040 molar raised to the 1/2 power. So now I'm going to divide both sides by my numbers to isolate k. And 0.04, raising something to the 1/2 power is like taking the square root. So this ends up being 0.20, and then I have a molar to the 1/2. Okay, so I'm dividing both sides by that, 0.040 molar and 0.20 molar to the 1/2. It's getting smaller and smaller. So we end up getting a k here, lowercase k, equal to 3.375. And the units are going to be, we have a molar down here. We'll cancel this molar up here. And we're going to be left with this guy, which is on bottom. So m to the minus 1/2, and this guy, s to the minus 1. And then I think I rounded this with respect to sig figs, because all these guys have 2 sig figs. So this would be 3.4 m to the minus 1/2 seconds to the minus 1. That is tiny little k. Okay, so hopefully that explains this problem a little bit better. Again, I'll probably start with this. I know people won't watch it at this point in time, but at least it's recorded, the solution to question 14.2.